Ok, buenos días a todos, buenos días en Juriquilla y espero que ya estén conectados en Hermosillo. La idea de tener al profesor Paul Renne el día de hoy fue apoyada por la Academia Mexicana de Ciencias dentro del programa de profesores distinguidos. Entonces el profesor Paul Renne nos ha hecho el favor de visitarnos. Tenemos una colaboración interesante con él. Estamos trabajando algunos aspectos relacionados con las ideas del volcán Popocatépetl. El profesor Renne es profesor de la Universidad de California en Berkeley, es director del Centro de Geochronología en Berkeley y tiene una muy amplia experiencia. Me tardaría bastante tiempo en describir, hablar de sus publicaciones. Es un investigador que tiene intereses bastante variados, amplios, pero también va a bastante profundidad. Como ustedes verán, tenemos también la invitación para que participen mañana en las dos charlas que va a dar, en donde vemos que su capacidad no solamente es en el área docente, sino también en el área de investigación, el desarrollo de metodologías asociadas a los fechamientos radiométricos, pero también en problemas geológicos específicos, como es el de la determinación del límite cretácico terciario, de lo cual hablará mañana, y muchos otros. Algunos de sus resultados más espectaculares en el caso de la volcanología fue el fechamiento de la erupción del Vesubio, lo cual fue bastante impresionante para muchos, de llevar la técnica de argón-argón precisamente a esas fronteras, ¿no?, bajo ciertas características. Entonces, le hemos pedido a Paul que diera este curso para poder manejar con mayor soltura algunos de nosotros los fechamientos de argón-argón. Entonces, pues los dejamos con el profesor Renne. Paul.
Okay. Muchísimas gracias, Hugo. Buenos días a todos. ¿Me pueden oír claramente o suficiente? Okay. Primero, eso no es muy estable. Ok, lo dejo. Quiero agradecer al Instituto, a la Academia de Ciencias, para el comité de dar este curso. Y bueno, desafortunadamente mi español no es muy claro y por eso yo voy a hablar en inglés. Pero si alguien tiene preguntas de clarificación de la ciencia, cualquier cosa, por favor. Ok, bueno, entonces la idea, my objective today is to give you an overview of the argon-argon geochronology technique, which is, as I will try to demonstrate, the most versatile dating method that we have. We have the broadest range of capabilities with this technique of any dating method. And you will not remember everything I tell you, I'm sure, but this is why I encourage you to ask any questions for any purpose as we go. And so if you just come away from this short course with a flavor, a general idea of how this works, I will consider it successful. There are lots of details, and I'm going to discuss some of the details, mostly so that you appreciate the complexity of this approach, but I also want you to realize that all of these details are manageable. So here we go then. Just to begin, I want to hopefully convince you and to demonstrate that the method of argon-argon geochronology has the greatest range of capability or applicability of any technique from 2,000 years ago, as Professor Delgado mentioned. This is the dating of the eruption of Vesuvius, which buried Pompeii, up until the age of the Earth. And actually, we have not been able to date the age of the Earth using this method, but we can date meteorites, which are essentially the same age. So between 2,000 years ago and 4.5 billion years ago, this technique has been applied. Also, very important is that there is no more precise method of dating rocks and events in this past than the argon-argon technique. And the potential accuracy, and by this I mean the correct results, not the precision, but the accuracy, is potentially. So the point I'm trying to make here is that the precision, the ability to distinguish one age from another of the argon-argon method is as good as any other technique, and the accuracy is potentially as good as any other technique. We'll discuss this in more detail, and I think you will understand what I mean when I distinguish between precision and accuracy. Another very important characteristic is that this technique allows us to date the greatest variety of rock types of any method available. So in the volcanic environment, which of course is very important here in Mexico, we can date essentially any kind of volcanic rock that you might have. Basalt, andesite, dacite, rhyolite, and all of the strange ultramafic, alkaline lavas, no problem. There are some age limitations, as we'll discuss, but the compositional range is huge, infinite, in fact. We can also date plutonic and metamorphic rocks, and in these kinds of rocks, what we obtain is not the formation age, but rather the cooling age, and we'll discuss in more detail what I mean by that. And so, from these kinds of rocks, plutonic and metamorphic rocks, we can date, typically we date minerals separated from them. So biotite, muscovite, alkali feldspar, plagioclase, and amphiboles are very commonly analyzed. And then finally, and this is one of the things that makes the technique very distinctive and very unique, is that we can also date sedimentary and autogenic minerals. So there are certain evaporites, for example, that we can date. Manganese oxides, which contain some potassium. And these are useful for dating climatic evolution. Minerals like alunite, which are often important for ore deposits, hydrothermal systems, and so forth. A great variety of minerals. The only requirement is that they have potassium. This is the important thing. So, in other words, this is a method that has this tremendous range of capabilities, and so it's really worth knowing about. In fact, if you had to choose only one technique to learn as a geologist, this is probably the most important one, unless you're super specialized in something else. Okay. So this is the outline of what I'm going to talk about today. We'll start with basic principles, and this has to do with the Potassium-Argon system, which is very closely related. Then the theory of the argon-argon technique, and how the argon-argon technique differs from the potassium-argon technique. Then we'll discuss a little bit about the actual measurement process and how we analyze the data. This will probably be, to some extent, I have to say, the most boring, the least interesting part, but it's very important. And then, of course, there's calibration, which is how we take the data, what we measure, after we make a number of corrections so that we are actually measuring the isotopic composition of a sample, then we have to somehow translate that to an age. And that's what I mean by calibration. And then finally, well, not finally, next we have also there are various ways in which the data can be combined to determine the age of rocks or minerals. And that's what I mean by age determination. And then I want to discuss one of the actual problems or limitations of the technique, which is what I call here the recoil problem. And this is actually something that we have some ideas. In fact, they're more than ideas. We have some techniques just developing now to reduce this problem. So I'll give you a taste of what's coming next, and I'll discuss this in more detail tomorrow, actually. And then finally, I'm going to discuss some applications. So some specific cases, which I think probably would be, in my opinion, will probably be the most interesting part. So we save that for the end. Okay. So the most important point to begin with is the fact that the element potassium contains a very small amount of the isotope of mass 40, potassium-40. Potassium has 3 isotopes, and the mass 40 isotope is the most rare, but it decays in a kind of a complex way. It has a natural radioactivity. On the one hand, it decays by beta emission, which is essentially the emission of an electron, to form calcium-40. I'll provide a little bit more detail on this. Okay, so as I was saying, the radioactive isotope of potassium, potassium-40, decays to calcium-40 by this process of beta emission. And in fact, this is the most important radioactivity of potassium-40. So, as you can see here, almost 90% of potassium-40 decays, and that turns out not to be very useful for us. Most of the potassium-40 decays to calcium-40, which is not very interesting for us. We have to somehow recognize this and account for it, but it's not the most important part of the story. So the important aspect of the radioactive decay of potassium is shown over here on the left side, and the most important one, what I was saying is that the most important decay for our purposes is this electron capture decay of potassium-40, which decays to an excited state and then emits a gamma particle and then decays to argon-40. So this is really the important path. There is also a very small amount of positron decay, which is basically a positively charged electron, which also decays to argon-40, but it's much less than 0.1%, so we can completely ignore it. It's irrelevant. And then some time ago, it was believed that there was another decay of potassium-40 by electron capture directly to argon-40 with no intermediate emission of a gamma particle, but we now know that this is not true, so this can be ignored. So the important things are, just to reiterate, this electron capture decay to argon-40, which accounts for about 10% of the radioactivity of potassium-40, and this one, which accounts for about 90%. So this, of course, is the basis for the Potassium-Argon dating method, and I'll talk a little bit more about that because it helps to understand the argon-argon method. It's in fact critical. But first, I want to just explore and discuss some of the criteria for whether or not a radioactive element, radioactive isotope, is useful for geochronology in general. And of course, the answer is going to be yes for the argon-argon system. But to get there, let's just consider, first of all, the half-life of the radioactivity has to be comparable to the event that we're trying to date. So, of course, if you look at the table of the nuclides, there are many isotopes that occur, they're formed by cosmic radiation or processes in nuclear reactors. Sometimes there are actually such things as natural reactors where you have high concentrations of uranium. And many of these radioactive elements decay so rapidly that they're not useful for geochronology. I mean, some of the half-lives are measured in seconds or nanoseconds. And of course, that's not useful for us. On the other hand, some half-lives are tens or hundreds of billions of years, and that's not useful for us either. So the half-life of the system that we're trying to use has to be more or less comparable to what we're trying to date. And by more or less comparable, I mean within a factor of, say, 100 or so. It depends on various criteria, but that's a general rule. Okay, secondly, the initial daughter has to be estimatable. And I'll clarify this as we go, but the point is that when we talk about, say, the potassium-40 decaying to argon-40, well, there's argon-40 in the world, in the atmosphere and in rocks, that's not formed by radioactive decay, and somehow we have to account for that. We have to have some means to do that. And in fact, I mentioned that the decay of potassium-40 to calcium-40 is not very interesting to us. And one of the reasons for that is that most calcium is calcium-40. 96% of all calcium has mass 40. And so if we tried to use the decay of potassium-40 to calcium-40 to date rocks, we would have to somehow know a tiny, tiny amount of calcium-40 produced by radioactive decay compared with what's already there in nature. And that turns out to be very difficult. So this initial daughter problem is really among the most fundamental things that has to be considered when you're thinking about using a radioactive isotope for dating. You also have to have enough of the parent isotope, and by parent I mean, for example, potassium-40. The parent isotope has to be present in enough concentration that it produces enough daughter isotope that you can measure it. That's pretty obvious. The daughter isotope, i.e., or in other words, argon-40, has to be stable. It should not itself be radioactive. The daughter should have only a single parent. In other words, if there was some other radioactivity that was producing argon-40, it would be difficult to determine which was responsible. So that's important. And then finally, both the parent and the daughter must be geochemically stable at the scale of analysis. And here I mean at the spatial scale of analysis. And this is sometimes referred to as the closed system requirement. So if you want to date a mineral, it cannot have either lost or gained the parent or the daughter. So this turns out to be an important issue too. So these are all the criteria that we have to keep in mind when we think about what makes a useful geochronometer. Okay, so one way to look at this is to consider what's called the chart of the nuclides, or table of the nuclides. And this is basically a plot of the number of protons on this axis versus number of neutrons on this axis. So the number of protons, of course, is what determines the chemical element. So as you go increasingly up in number, the element changes. And as you change the number of neutrons, this just determines the isotope of interest, but the chemical element is the same. So, for example, here's potassium. And potassium has all of these isotopes are known, but if you look at the color coding, potassium of mass 38 has a half-life between 1 minute and 1 hour. Potassium 39 is stable, which is what blue means. And potassium-40 is radioactive with a very long half-life. That's the one we know. 41 is stable as well, and so on. And these are all radioactive with timescales that are too short to be useful for us. So this chart of the nuclides is a useful way to look at what the process of electron capture decay involves. So electron capture is a process by which an orbital electron around the nucleus of a potassium atom actually falls into the nucleus and combines with a proton to form a neutron. So you gain one neutron and lose one proton, and that means that on this chart of the nuclides, you go down one proton and increase one neutron. So I find this a useful way to think of different radioactivities. And then in contrast, here's what beta decay does. Beta decay, as I said, is essentially the emission of an electron, and that converts a neutron into a proton. So you lose one neutron, gain one proton, and that means you go down in the number of neutrons and up in the number of protons. So there's the calcium-40. This is just another way to visualize the decay. Okay, so before we start thinking about any radioactive decay process for using as a geochronometer, we also have to think about some of the general characteristics of those elements, not just the isotopes, but the elements as well. And so just to have an idea about that, here are some vital statistics for potassium. Most potassium is mass 39. A very, very small portion is mass 40, and an intermediate portion is mass 41. Now, many people think when they see these figures, they assume that the reason there's so little potassium-40 is because most of it has decayed away to argon and calcium, right? That seems logical. But in fact, that's not true. That's not the reason why it's so little in abundance. The reason is that during the process of creation of the elements, this is very improbable production by nuclear fusion. It's not favored by the process of star formation. So it has always been rare since the very beginning of the formation of the elements. In general, potassium is relatively abundant in the crust, as most of you know, averaging something between, say, 0.5% or 2% by atomic percent. It does not undergo any isotope fractionation in terrestrial environments to within the ability to detect this kind of fractionation, which is about the 0.6% level. So what do I mean by isotope fractionation? Does anybody know what I mean when I say that? No? Okay. You do, but you're embarrassed to ask. Okay, I'll say anyway. So isotope fractionation means during some chemical processes, for example, the crystallization of a mineral from a magma. In some processes, certain isotopes are favored over others. So typically, in a crystallization process, the heavier isotope, the more massive isotope, will enter the solid phase, and the lighter ones will be partitioned into the liquid phase. The same is true when you form, say, calcium carbonate from seawater. So the point is that nobody has observed any preferential bias in the isotope composition of potassium. So that's one thing we don't have to worry about, at least at this level, at the 0.6% level, which increasingly is something that really needs to be investigated further, because 0.6% used to be a perfectly good, safe number, but now we're pushing the limits and asking much more of these techniques. And so this is an area that really should be further investigated. And one of the reasons I say that is that some significant fractionation has been found in the lunar regolith, where impact processes are very important, and volatilization of elements is a very important process. And in volatilization or vaporization, fractionation has been observed, and at the more than 1% level, which is pretty significant. So one might imagine that in the early Earth, when there was a large flux of meteors hitting the Earth and lots of this vaporization going on, there might have been some more significant fractionation of potassium. Just something to keep in mind. Okay, so looking at the same sort of analysis for argon, most of the argon that we have any contact with is in the atmosphere, where it is actually the third most abundant element, in the atmosphere, nitrogen, oxygen, and argon, with 0.7%. And almost all of that argon is argon-40. Now in this case, the fact that argon-40 is overwhelmingly dominant over the other two isotopes is because it has been produced by radioactive decay of potassium. The next most abundant isotope is mass 36, and then mass 38. And these two isotopes can be produced by cosmic radiation, particularly on calcium, but not typically in concentrations that are large enough to worry about for our purposes. Now, you might wonder, who cares about these two? What we're really concerned with is this one. Well, we do have to worry about these, and I'll come back to that. So, the atmosphere is a very, very homogeneous, at least in terms of argon, reservoir. The isotopic composition of argon in the air has these percentages basically anywhere in the atmosphere. And because the atmosphere is in communication with the oceans, seawater is very homogeneous and has this composition as well. And but beyond that, it's very difficult to specify what the argon concentration is in rocks because it depends on their age. So the one really can't give any sort of crustal or mantle concentration numbers. But here's one of the important questions. If we're concerned with dating rocks on the Earth, any rock that we could possibly collect on the Earth has been in contact with the atmosphere. Not just when we sample it, but potentially during its formation. And so it's very difficult to completely eliminate this atmospheric component of argon. So this is something we're going to have to take into consideration. And that's why I call it the initial argon problem. So this is just a special case of what I called the initial daughter problem earlier. Okay? So now, the basic rule of radioactivity, the basic rate law, is extremely simple. And I'm sure many of you have actually solved this problem in your calculus class. And it was first written in this very simple way more than a century ago by Rutherford and Soddy in 1903. So stated in English in this case, this rate law says that the rate of change of the number of atoms of a radioactive element as a function of time is proportional to the number that are present at any time, t. And this constant of proportionality is what we call the decay constant. And this minus sign indicates that it decreases. So this very simple equation can be solved easily to yield this expression. The number of atoms at any time t is equal to the number that you started with at time 0 times e to the minus lambda t, where lambda is this constant of proportionality, or we'll just call it decay constant, times the time elapsed. So one of the things that's really remarkable about this very simple expression is that it's true for any radioactivity, for electron capture decay, for beta decay, for alpha decay, which is important for uranium, for fission, such as what produces fission tracks. So any of these processes of radioactive decay obey this same law, which is a pretty remarkable thing. Okay, so now a little bit of arithmetic. Sorry for this, but we can just skip through it. So we can rewrite that basic equation, and now we introduce the parameter d to represent the daughter. So this is the number of daughter isotope atoms. And this d star, d estrella, is the number of radiogenic daughter isotope atoms. So this is some fraction of this. And, oh, this should be a subscript 0. Sorry, the initial number of daughter isotope atoms. Yeah, this should have a 0 here. And then this is the number of parent atoms of the radioactive parent isotope. And then we're also going to use the term C, which is the number of a common isotope, number of atoms of a common isotope, which will be of the same element as the daughter. So just to follow the example using the potassium-argon system, a common isotope here might be argon 36. It doesn't increase by radioactivity, and that's what we mean there. So that equation that I showed you on the previous slide can be solved for T very simply, and with these definitions, this very simple generic age equation is derived. So this says that the age of a sample is equal to 1 over the decay constant times the natural logarithm of the quantity 1 plus the ratio of the radiogenic daughter isotope to the parent isotope. So this is true for any radioactive system. So that's why I say generic age equation. Now we have to take one little extra step if we're talking about the potassium-argon system, because remember that the potassium-40 that we're concerned with decays not just to argon-40, but also to calcium-40. So to account for that, we have to use this so-called branching ratio, which is the total decay constant, which is equal to the sum of the two, divided by the electron capture decay constant. Otherwise, this is the same as the generic age equation. So in a practical sense, the way that we use this relationship is that we measure the potassium, or rather the argon-40 in a sample by a process called isotope dilution. And I'm not going to elaborate on that because it's really not critical to understand the rest of what I'm going to tell you. But it's a well-established technique for measuring concentrations of isotopes. And then we have to measure the potassium-40 using different methods, typically by a technique called flame photometry. And we have to then have a large enough sample that we can take some of the sample and measure the argon-40 concentration in it, and then using these other techniques, measure the potassium concentration in order to derive this ratio. And furthermore, what is typically done is the potassium is not measured, the potassium-40 is not measured directly, but rather we just measure the total potassium content and then use the isotopic composition that I mentioned to you earlier and say that such and such proportion of the potassium is potassium-40. Well, such and such is 0.0117%. And because we know that potassium is quite homogeneous isotopically, that's a reasonable thing to do. So that's how the potassium-argon system works, and I think that's all we're going to say about it, directly anyway. Except for the fact that this equation, of course, is in terms of the radiogenic argon-40 in a sample. And when we measure a sample, measure the argon-40 in a sample, we're measuring the total argon-40. We can't distinguish between how much was created by radioactive decay versus how much was already there. There's no way to do that. And so, what we commonly do, I say we, I don't actually use this technique anymore, but what is done is to assume that all of the argon-40 in a sample that is not due to radioactive decay, is in fact contamination from the atmosphere. And so we observe that the argon-40 to 36 ratio of the atmosphere, as I said, is very homogeneous, and it has this ratio. So we can simply calculate the amount of argon-40 that's radiogenic in a sample by taking the total amount of argon-40 and subtracting 298.56 times the amount of argon-36 that we measure. It's that simple. So that's the so-called air correction. Now, you might well wonder, and you should wonder, if this is always true, if all of the non-radiogenic argon in samples always has atmospheric composition. And the answer is definitely not. So this is one of the fundamental problems with the potassium-argon system, is that sometimes there is more argon-40 that was initially present than can be accounted for by the atmosphere. And in very rare cases, there's less. And this requires some very special circumstances. It's very rare. But to find non-radiogenic 40-36 ratios greater than the atmosphere is really not very rare at all. So this is a fundamental problem with the potassium-argon technique. And it's a problem that depends to some extent on the geologic environment. So in rocks that have been substantially exposed to the atmosphere during their formation, such as a lava flow, it's usually a pretty good assumption. But in deep, high-pressure rocks like metamorphic rocks or plutonic rocks, where there's argon with isotopic ratios that may be much greater than this, the initial ratio may be much higher. So that's something that you really have to worry about if you're a potassium-argon person. Okay, now I think that's all I'm going to say about potassium-argon. No, not quite. One way, there is one way that one can actually solve that problem and do a little bit better than simply assuming that non-radiogenic argon has atmospheric composition. And that's the use of what are called isochrons. Isochrons are probably familiar to many of you. They are commonly used for systems like the rubidium-strontium system or samarium-neodymium or lutetium-hafnium, but they're really not very commonly used in the potassium-argon system. But it still helps to illustrate a point. And that point is this, that we can take one of the earlier equations that I showed you, whoops, which is the number of daughter atoms is equal to the number that you started with, plus the number that are radiogenic, that's obvious. And then we can substitute in this expression for the number of daughter atoms as a function of time. And now if we take both sides of this equation and divide through by this common isotope, which in the case of argon might be argon-36 or argon-38, either one would work. We divide through by some common isotope, and then notice that this now is the equation of a straight line in which this would be the intercept, and this would represent the slope. And let me illustrate that. It's much easier to do if you see the relationship. So if we make a plot of the daughter isotope over the common isotope versus the parent isotope over the common isotope, this is what you would get. This is the equation of a straight line. And the intercept of that straight line gives you the initial daughter concentration divided by the common isotope concentration. And the slope gives you this expression, which can be simplified. It's very closely equal to just the decay constant times the age. So if you have a suite of samples from a given rock, let's say we analyze several minerals from, let's say it's a granitoid. So we analyze the hornblende and the plagioclase and the biotite and the potassium feldspar. Then we might get a relationship that's this simple. But that would require that they all have the same initial ratio of the daughter isotope to the common isotope. So that's one requirement. And then there has to have been no disturbance of any of those minerals since the time it formed. And that's pretty uncommon with the potassium-argon system. And this is why the isochron technique is not really commonly used in the potassium-argon technique. It has been used, and it has been used successfully, but it's not routine. It's also quite a lot of work. There are a lot of analyses required to generate this much information. Okay. Wait a minute. Okay, so I'm sorry, I pressed the wrong button. This actually shows the isochron basis, not in terms of the generic daughters and parents and common isotopes, but in terms of real argon isotopes, but it's the same thing. Notice, though, that we have to take account of the fact that this potassium-40 is decaying not just to argon-40, but also to calcium-40, and that's what this branching ratio does for us. Okay, now one important thing to think about when you think about isochrons, because as I say, they're not terribly important for the potassium-argon system, but they will become more important in the argon-argon system. And that's why I'm taking the time to develop this concept now. One of the important considerations that has to be borne in mind is whether, in fact, a set of analyses of a sample do define a straight line, because the extent to which they define a straight line is a measure of how reliable the initial composition is and how reliable the age is. So in other words, you can imagine if the points scatter a lot about this isochron, this line itself is called the isochron, if there's a lot of scatter about that, at some point, probably it has less meaning and the uncertainty will be much larger. So the method that's usually used to determine that is what's called the MSWD, and this stands for mean squares of weighted deviates. Most people don't know that. Even geochronologists don't know what MSWD stands for. We use it all the time. But the definition is very simple. It's given by this equation, but just to make it more conceptual, it's the ratio of the scatter from the isochron of the individual points to what would be expected for the uncertainties of the individual points. So it's the ratio of scatter to precision of the analyses, the average ratio. So if the scatter about an isochron line is exactly consistent with how precise the measurements are, this value of the MSWD, does anybody know what that would be? It's 1. So an MSWD value of 1 is ideal, that's perfect. An MSWD value much greater than 1 means that there's excess scatter. You cannot explain the scatter from the precision of the individual measurements. And an MSWD less than 1 means the data are too good. There's too little scatter. And this can happen because, well, in the worst case, if somebody made up the data, but let's assume that never happens. If somebody overestimates their uncertainties of their measurements. So, and this happens sometimes, if people are too conservative and they assume that their uncertainties are much larger than they actually are, you can, first of all, that will give you a very small MSWD, and it will also allow you to infer that an isochron is valid. So this is probably the most common problem. So this MSWD statistic, for those of you that are familiar with some statistics, it's equivalent really to a chi-squared parameter. Okay, so there we have isochrons, and we'll come back to them. And so that's basically the first chapter, if you like. The basic outline, basic principles of the potassium-argon system. So now we're going to talk about the argon-argon method, which is really what we're here to talk about. And before I get into that, I'll mention a little bit of history. The potassium-argon method was really invented in the late 1940s and became more widely applied in the 1950s, and it started at the University of Chicago. The argon-argon method was invented in about 1965 in my university in the physics department, which is where most of the first major discoveries in isotope geochemistry and mass spectrometry and geochronology were made. They were made in physics departments with little funny homemade mass spectrometers and things like that. So in the mid-1960s, in the physics department of Berkeley, there were a couple of postdocs who were looking at xenon isotopes in meteorites, and they irradiated their samples in a nuclear reactor, and they found something really funny. They found argon of mass 39. Now, I showed you the abundances of atmospheric argon isotopes, and the only naturally occurring argon isotopes in the atmosphere, or to most extent, anywhere in the Earth, are argon 40, 38, and 36. So they discovered argon 39, and they thought, aha, what does this mean? They figured out what it meant, and that's really how the method was originated. So let's look at that in a little bit more detail. So we've already gone through this. This is just another way to visualize the basic radioactive decay scheme of potassium-40. One branch goes to argon 40. Here's the electron capture decay constant, and this is its nominal value. I'm going to show you later some different values. And here's the beta decay branch to calcium-40, and all of this we've already been through, except that I haven't given you these numbers yet. One thing now, for the first time I'm showing you, is the half-life, and that is equal to the natural log of 2, natural logarithm of 2, divided by the total decay constant. So the total decay constant is a measure of how fast potassium-40 decays to anything. And the beta decay constant is how fast it decays to calcium-40, and the electron capture decay constant is how fast it decays to argon-40. So the total half-life of potassium-40 is given by this number, and it's about 1.25 billion years. Okay, so just keep that in mind. And as I said earlier, the half-life of interest should be comparable to the processes that we're trying to date. And in most cases, a billion-year half-life would make it very, very difficult to date things that were as young as a few thousand years or a few tens of thousands of years. The only reason we can do that in the case of the potassium-argon or the argon-argon system is because potassium is so abundant in the Earth. So we're kind of fortunate in that respect. So that's the total half-life. And now the basis for the argon-argon system is, as I said, following up on this discovery in the mid-1960s, that in a nuclear reactor, you can make potassium-39 into argon-39. So argon-39 is what these physicists discovered. And the basis for the whole technique is that instead of measuring the potassium-40 as potassium, you convert some of the potassium, mass 39, into argon. And so this is a proxy for this because of this constant isotopic ratio. And this then becomes a proxy for this. So this is a measure of this, which is a measure of that. So there's two steps of indirect reasoning here. This step is secure at the 0.6 or better percent level, as I mentioned earlier. And this step really depends on the experimentalist, how well we can measure the argon-39 and how well that represents the amount of potassium-39 is up to us. Okay, everybody follow that so far? Okay. So when we irradiate potassium in a nuclear reactor, and that's a reactor that's powered by uranium-235, and uranium-235 undergoes fission, and that produces neutrons. So in a nuclear reactor, the amount of argon-39 that we produce is a function of the amount of potassium-39 in the sample. And remember that potassium-39 is the most abundant isotope of potassium. This is 96% of all potassium. Times delta, which is the duration of the irradiation. So that's just time. So obviously the longer you irradiate a sample, the more argon-39 you produce. And then this is the messy part, times the integral of what's called the neutron capture cross-section times the neutron flux, both as a function of neutron energy over the entire energy spectrum. So let's take this apart a little bit so you understand what the individual things mean. So the neutron capture cross-section is basically the probability that you will produce argon-39 from potassium-39 at a given energy of neutrons. So some neutrons with higher energies are more probable to produce argon-39. And we'll go into that a little bit more later on. So this is just a probability of the reaction occurring, and this is the neutron flux at that energy. So the neutron flux is just how many neutrons per unit time are being experienced by the sample. So if we just multiply this over all energies, or actually integrate it, that is what we're doing here. So depends on the amount of potassium-39, the duration of the irradiation, and this integral. Okay. So to actually apply this to dating, what the early pioneers of the technique did, and we still use this today, although there are other ways to do it, but we define a parameter called J, which is defined in this way. And it'll become more clear why we do this in a minute. So if we just solve for this for the argon-40 radiogenic to potassium-40 ratio, by substitution and solving for this ratio instead of J, this is the expression we get. And what this number qualitatively means, J, it's a measure of the extent to which you've converted potassium-39 into argon-39. So it's a measure of how how much argon-39 you've made per unit potassium-39 that you started with. So we've made this definition, and that lets us write the age equation. And I'm skipping lots of little steps here, but it's just arithmetic, and you could do this yourself based on what I've given you. But just to get to the more interesting aspects, we'll go straight to the age equation, and it looks very much like the generic age equation, except that now we have this parameter J involved here. And notice that we have also the total decay constant, just as with the potassium-argon equation. But now we have only two isotopes of the same element, argon-40 and argon-39, to worry about. Now here this is radiogenic argon-40, of course, so we still have to worry about the initial daughter problem. And I've subscripted the argon-39 with a K to indicate that this is the argon-39 that comes from potassium, that we made from potassium. Turns out that we make a little bit of argon-39 from other elements, and we'll come back to that. But this just is to indicate specifically the argon-39 that comes from potassium. So the fact that we can now measure basically the ratio of two different isotopes is a huge advantage compared to having to take a sample and take some of it to analyze for potassium and assume that the potassium has the normal isotopic composition, and then take another portion of the same sample and measure the argon concentration. First of all, doing it that way requires that you have a relatively large sample. So for potassium-argon dating, you need something on the order of 50 to 100 milligrams at least. That's a fairly large sample. Using this technique, because we can measure all the information we need just from the mass distribution or the mass spectrum of one element, we can analyze much, much smaller samples. So that right away is one of the huge advantages of this technique. And we'll come to several of the other advantages as we go. So this is the basic age equation. And we still have to contend with this initial daughter problem. So in many applications, we make this atmospheric or air correction the same way we did with potassium-argon. But there are some other more powerful approaches. But first, I want to come back to this parameter J. So remember the funny definition of this parameter J, and it involves this integral of the capture cross-sections times the neutron flux over all neutron energies, which is basically extremely difficult to actually measure that with any sort of precision. We don't actually do that. We don't actually measure that, fortunately. What we do is we just solve the age equation for a standard. So when we irradiate a sample, we also irradiate standards of known age, and then we calculate this parameter J from the analysis of the standard. So this is just solving the same age equation for J, but now we can substitute in the age of the standard, which, as I say, we know, and it becomes this simple. So that's how we actually calculate J. So we're going to talk more about standards in a bit, but let me just mention also that another term that's used for standards is neutron fluence monitors, because that's really what they are. They're measuring the total number of neutrons that drive the reaction of interest. So that's how we actually determine J. And the value of J is basically a very straightforward function of the duration of an irradiation. If you remember from the first equation that I showed you, the rate of conversion, or the extent of conversion of potassium-39 to argon-39 is a function of time. So for a given reactor, that is basically a linear relationship. Wow, how did I jump so many? There we go. Such that in a very, what I would call a hot reactor that has a very high neutron flux, the J per hour is high. For a wimpy, or it's a kind of a silly name, a weak reactor that has a low neutron flux, the rate of conversion, the J per hour, is relatively low. Now, one of the things to keep in mind is that there's only so much range in isotope ratios that we can measure, and I'll give you an illustration of that in a minute. But we want to try and keep the ratio of argon-40 to argon-39 in a sample that we measure to within some tolerances, say between 100 and 0.01, or maybe between 1,000 and 0.001. So a factor of 10 to the third, or a range of 10 to the sixth, ideally. And so we can't control, in a given sample, we can't control how much argon-40 there is, but we can control how much argon-39 there is, simply by how long we irradiate it. So for very old samples, we need to irradiate them for a very long time. And that's an important thing to keep in mind. It's a practical consideration. For example, if you want to date some rocks, and you communicate with somebody who does this, and they say, well, yeah, I can date your sample for you, but it's going to take 6 months. And you say, what? Why 6 months? Well, it's because if it's a very old sample, it takes a long time to irradiate it. And then after a sample has been irradiated, of course, it becomes radioactive. So you have to let the short half-life harmful radiations decay away before you can handle it. So in many cases, you might have to irradiate a sample for 2 months if you're doing meteorites, for example, which are very old. And then you might have to let it decay for 2 months or more. So that's why the long time scale for this process. Fortunately for younger samples, at the other extreme, even in a very wimpy reactor, very often for quaternary samples, say less than 2 million years old, you can irradiate a sample for something like 15 minutes or 30 minutes, and then you let it cool for, say, 2 weeks, so you can actually analyze the sample within a month. So by my standards, a month is very short, not for other techniques, I suppose. But so that's some basic practical information about this J-value business. So the one important issue is how the standards are placed in a reactor relative to the samples. And this is important because the more standards you have bracketing samples, the better you will be able to know the J-value. And that turns out to be an important factor in the uncertainty of an age, is how well you know this J-value. So the old-fashioned way, which is disappearing really, but some people still use it, is to take aluminum foil packages, which are about 1 centimeter in dimension, and put the samples in the packages and stack them up, and every so often, say here, 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 and here, you put some standards. And the standards then you analyze to get the J-value, and so a typical situation would be something like this. So this is J as a function of this vertical height, and it goes through a maximum about in the center, and then you just fit a curve to this and interpolate to assign a value of J to each of these individual packets of samples. And that's okay if you're really only concerned about getting a J-value to with a relative error of about 1%. But that's really not good enough for most modern work. And so now we have schemes like this where we have aluminum discs that have little wells drilled into them, and standards are placed like this, and then these discs might be stacked up, say 1 to 10 of these. Now what's important about this approach, not only do you have more standards, you have one standard at every level, but you also have some measure of the horizontal neutron flux variation, which this approach doesn't allow you to do. And the horizontal variation can be pretty significant. There can be as much as about 0.5% variation across one of these disks. And we often are aiming for something like 0.1% precision. So we really need to do this. So this is really increasingly the modern way to do it. Okay, so one of the considerations that I mentioned in terms of radiating samples and standards is that you need to try and control the ratio to some extent. You don't want to have to measure an argon 40 to the argon 39 ratio of 1 million, for example. And I'll show you why that is in a minute. But one of the ways that we look at this is in terms of what I have termed the R values. And this is a fairly new concept, but what it is, the definition of the R value, and this is going to be important later on, it's the ratio of the argon 40, radiogenic argon 40 to potassium-derived argon 39 in a standard relative to that same ratio in a sample. Actually, more often we flip it around. It's this ratio in a sample relative to that in a standard. But if we were to, say, try to analyze a 2,000-year-old sample, like the eruption of Vesuvius that destroyed Pompeii, and we used a standard which is called MMHB, it's a hornblende standard, which is about 523 million years old, the R value, the ratio of these numbers in the sample, this 2,000-year-old sample, relative to this standard would be about 300,000, 3 times 10 to the 5th. And that's a pretty big number. That's a difficult thing to measure for reasons I'll show you in a minute. So a better standard to use would be one that is very widely used called the Fish Canyon sanidine, and it has an age of about 28 million years. Now we're able to measure an R value of something more like 10 to the 4. Better yet would be a 1.1 or 1.2 million year old standard, which is also a sanidine, which would let us measure an R value of about 600. So the closer this R value is to 1, the easier it is to measure, so the more precise the result will be. And we're going to talk more about standards a little later, because this is one of the main components in the calibration of ages, how we derive ages from argon isotope data. So just to illustrate the point about measurement difficulties, this is a typical mass spectrum. So this is what one actually measures in essence. And this is not a real spectrum. This is just drawn by hand. So this shows the argon 40 peak, 39, 38, 37, and 36. So right away you can tell that because we have argon 39 and 37, that this sample has been irradiated. And you can see that the argon 40 is the biggest peak, which is usually the case. And it's a little bit broader than the argon 39 peak, a little bit wider because it's more intense. Now what happens if the argon 40 peak becomes much, much larger than the argon 39 peak is that you start to have the tail of this peak starts to actually overlap the adjacent peak. And that actually creates a false contribution to this peak. So that's why we don't like to measure extremely large ratios of two adjacent isotopes, because of this so-called peak-tail effect. Now there are various techniques that one can use to extrapolate the tail, to mathematically create a curve that does something like what you expect it to do, and then subtract it. But there's no real a priori way to know what this looks like. So it's just a model, and it's better to just avoid it, having to do that.